Hello everyone, my name is Álvaro Beizaga from the University of Luxembourg, and I will present our journal first paper entitled On Systematically Building a Controlled Natural Language for Functional Requirements. This work has been done in collaboration with Mauricio Alferez, Damiano Torre, under the supervision of Lionel Briand and Mike Sabet-Sabet. Requirements are crucial in all software and system development projects because they state the necessary characteristics and qualities of a system. Most software requirements specifications are written in natural language. Some studies confirm that 71% of software requirements are written in natural language. This is because natural language can be used in all application domains and understood virtually by all project stakeholders. The quality of a software system greatly depends on the quality of its requirements. High quality requirements are those that are precise, consistent, and complete. Good requirements improve the system quality, the return of investment, and the customer satisfaction. On the other side, having missing, vague, inconsistent, or inadequate requirements has ripple effects in the entire software development process, causing projects to fail, excessive maintenance costs, or disappointed business users. The problem we address in this paper was motivated by practical need observed across many industrial domains. For example, in Clearstream Services Luxembourg, a post-trade service provider, our industrial partner, the current practice is to write system requirements using a general-purpose text editor without enforcing any requirement structure. Clearstream reported us that several communication and delays arise from requirements that are not stated precisely enough. In this paper, we develop a controlled natural language for writing requirements for financial applications. Controlled natural languages strike a balance between the usability of natural language and the rigor of formal languages. Furthermore, controlled natural language provides structure with specialized concepts and constructs that enable automated analysis, for example, extracting models from natural language requirements. To achieve our objective, we develop a systematic methodology to define our controlled natural language. This is an overview of our semi-automated analysis procedure to define our controlled natural language. It has 5 steps: extract requirements, identify codes, label requirements, group requirements, and create grammar. In the first step, we automatically extract natural language requirements from 11 software requirements specifications. In the step 1, we read the 11 software requirements specification and automatically extracted 2,755 functional requirements. The structure of the software requirements specifications clearly separates functional from non-functional requirements. We also verified that the content of the requirements was correctly captured by our automatic extraction algorithm. If there was any error, we manually corrected it. Once we extract a set of requirements, our next steps is to identify the codes. We follow a semi-automated process to identify codes and their corresponding verbs. In our context, a code identifies a group of verbs that share the same information content in a natural language requirements. Most of our codes are pre-existing verb classes from a well-known lexicon named Burnett. First, we extract the main verb of each requirement and obtain their lemma. A lemma is the base form of the verb. Second, we retrieve for each lemma its corresponding Burnett class. We can have 2 scenarios. First scenario, when there was a Burnett code available for the lemma. For instance, in the example, the lemma generate belongs to the Burnett class in gender 27. We store the Burnett code along with the lemma. And in the second scenario, when the lemma was not a member of any VERNet code in VERNet, then we try to associate any of the relevant synonyms of the lemma to a VERNet class. If there was a match, then we store the VERNet code along with the lemma. Otherwise, we propose a new code. For example, the lemma synchronize did not belong to any VERNet class. No applicable synonym belongs to any VERNet class. Then, therefore, we propose the code synchronize. At the end of this step, we obtain 41 codes. 32 codes correspond to VERNet classes from VERNet, and 9 are codes that we propose. We use the 41 codes that we identified in the previous step to label requirements and then group the requirements that share the same code. We manually label the requirements extracted in step 1 with the codes identified in step 2. For instance, in the example, we identified that the verbs used in the requirements are send and forward. These verbs belong to the code send 11.1. Therefore, we label these requirements with that code. Once we have labeled all the dataset, we group requirements that share the same code. Having the requirements grouped by label makes it easier for us to identify common information content among requirements. For instance, for the group requirements send 11.1, we can identify common information content such as actor and destination. In the last step of our analysis procedure, we iteratively created the grammar rules for our control natural language. To create a grammar rules, first we identify semantic roles and keywords in one group of requirements. We identify the correspondence between the semantic roles from the VERNet class code in VERNet and the parts of natural language requirements that represent the semantic roles. For instance, the syntax related to the VERNet code send 11.1 contains the preposition to and the semantic roles agent, which is a participant that initiates an action, theme, an entity which is moved by an action or whose location is described, and destination. We associate the VERNet semantic roles to parts of the requirements. When some content in the requirements was not related to any VERNet semantic role, we propose a new semantic role to identify that content. For instance, we could not associate the modal verb and the article to any semantic role of VERNet. Once we identify the content of requirements related to one of the groups of requirements, then we derive a grammar rule, our grammar rules. The grammar rules define the order of appearance of the content in Rimay that we previously identified. Moreover, we added a complete list of all the verbs members, and we added other generic rules. Once the grammar rules were finished, we checked that our grammar rules were expressive enough to allow us to write all information content. If the grammar was not expressive enough, we analyzed and extended the grammar. We followed this process in an iterative and incremental manner. And we created all the grammar rules of our control natural language in the same way. We name our control natural language Rimay, which means language in Quechua, an indigenous language spoken in some countries of South America. This is an excerpt of the grammar rules of Rimay. The rule requirement provides the overall syntax for a requirement in Rimay. The rule shows that the presence of the scope and condition structure is optional, but the presence of an actor, modal verb, and system response is mandatory in all requirements. In the example, we have a scope, which is a phrase that delimits the effects of the system response, followed by an actor, which is a role played by an entity that interacts with the system. And we have a modal verb, and then a system response that allows the user to express the behavior of the system. A system response is composed by an action phrase. An action phrase is a grammar rule that defines the order of the appearance of the information content that describes the action. After our analysis procedure, we have 48 action phrases. If we compare Rimay with existing patterns like years or wrap, these templates provide general constructs and concepts to specify requirements. However, these templates are not amenable to the type of analysis enabling task automation because they allow the introduction of unstructured text. Our control natural language Rimay enables users to write structured requirements by providing a structure with more specialized concepts and constructs, enabling task automation. We acknowledge that some of the Rimay structures were inspired by years. Rimay also supports 5 types of conditions. 4 out of 5 were inspired by the years template. The when structure is used when a specific triggering event is detected at the system boundary. The if structure is used when a specific trigger event happens or a system state should be held at the system boundary before triggering any system event. And the temporal structure to be used when the system response are triggered before or after an event responses. In these presentations, we only show a small part of the grammar rules. Please refer to our paper to obtain the full list of the grammar rules. For our empirical evaluation, we consider 2 research questions. The first one is about determining how well our control natural language Rimay can capture requirements of previous unseen documents. And the second research question is about finding the point in our evaluation where enough system requirements specification content has been analyzed to ensure that Rimay is stable for specifying requirements for the financial domain. To answer our research questions, we conducted an industrial case study with our industrial partner ClearStream Luxembourg. To answer our research questions, we follow an iterative process. Step 1, extract requirements. We collect a new unseen SRA, a software requirements specification document, and extract its natural language requirements. In the step 2, rephrase requirements using Rimay, we attempt to rephrase the extracted requirement of step 1 using our control natural language Rimay. We always maintain the intent of the original requirement. We also, in this step, keep track of the requirements that were not representable, as well as the causes for such limitations. In step 3, improve Rimay, we analyze the requirements that were marked as non-representable and enhance Rimay to make these requirements representable. And step 3, check Rimay's stability. This step verifies whether there was a significant change in Rimay's capacity to capture the content of previously unseen natural language requirements. If there is no significant change, we say that Rimay is stable and we stop the evaluation process. Otherwise, we iterate over step 1 to step 4 using a new software requirements specification document until Rimay becomes stable. In total, in our empirical evaluation, we did 4 iterations until reaching saturation. In order to answer our first question, how well can Rimay express the requirements of previously unseen documents, we calculate the number of requirements that were rephrased using Rimay. The table shows that Rimay is expressive enough to capture on average 88% of natural language requirement statements in for previously unseen software requirements specification documents from the financial domain. Subsequently, we analyzed the non-representable requirements, the 55 requirements, and we annotate each requirement with one of the following three causes. Cause one, the requirement contains a verb that is not supported by Rimay rules. Cause two, part of the requirement, excluding the verb, includes information content that is not supported by Rimay. Cause three, the meaning of the requirement is unclear and no financial analyst could clarify. After each iteration, if we did not reach our saturation point, we address the non-representable requirement labeled with cause one and cause two, but by updating existing grammar rules of Rimay or creating new ones. Requirements labeled with cause three were not addressed in Rimay. In the example, for instance, no business analysts were able to provide a more precise system response because they did not write the requirement. After analyzing three SRAs, we did not update Rimay because we reached saturation. In order to answer our second research question, how quickly does Rimay converge toward a stable state, we use the notion of saturation to determine the point in our evaluation where we have analyzed enough software requirement specification content to ensure that Rimay is stable for specifying requirements for the financial domain. In our evaluation, the saturation point is reached when all the verbs analyzed on requirements are already considered by the grammar rules of Rimay. We reach a stable version of our grammar after analyzing three software requirements specifications from our evaluation set. During the analysis of the four software requirement specification, no new verbs emerged. We therefore conclude that we have reached saturation. We use statistical tests to confirm that after analyzing three SRAs, changes to Rimay did not bring any significant improvements in the expressiveness of Rimay. As conclusions, we point out the following aspects. The ultimate quality of a software system greatly depends on the quality of its requirements. Controlled natural languages, compared to conventional requirement patterns, provide structures with more specialized concepts and constructs. Controlled natural language strike a balance between the usability of a natural language on the one hand and the rigorous of formal language on the other. And using controlled natural language enable automated analysis such as test case generation and model generation. Our evaluation shows that Rimay is expressive enough to capture most of the unseen requirements from the financial domain. Few requirements cannot be expressed using Rimay, and these experiments results indicate that Rimay is useful for improving the quality of requirements. Thank you very much for your attention.